Okay friends, so after we have completed the crystal lattice system, packing fraction, packing density of things like BCC, FCC, simple cubic system, and also we have covered up the hexagonal close packing. So hexagonal close packing fraction I have already covered up due to the reason that I may not get an opportunity to cover up while I discuss the hexagonal close packing in 3D. So you have already known how to calculate the packing fraction, the relationship between R, that is radius of the atom, A, that is age of the unit cell, and age means side, okay, and your D, that is nearest neighbor. So these all the things you have already calculated and the theory part is done. Now the next part which we are going to do now is the close packing in crystalline solids. So till now we have studied that about the unit cells, the basic unit cells, that is the FCC, BCC and simple cubic cell, and we have also done HCP. Now we will be coming now with each unit cells, how do we form the lattice or the crystalline solids. So what kind of packing that takes place of each unit cell so that we get a crystalline solids, and intricacies into it we are going to understand. Very simple things. Remember, in solid state there are 2-3 things that is very important. Number one is coordination number, very important term. Okay, coordination number is basically the number of atoms a single atom is attached to it. Okay, so it's like if I take Na(CN4), then we say that the coordination number of nickel is 4 because it is attached with 4 cyanide groups, right? So similarly, in case of crystalline solids, the coordination number is the number of neighboring atoms it is attached with or it is in contact. Okay, so one by one we will understand how the packing happens in a crystalline solid. So first thing we have to know is packing in one dimension. Packing in one dimension means dimension. What does dimension means? Either x-axis, y-axis or z-axis. One dimension means we have to take only one axis. So we will take over here x-axis. So this is the kind of packing they are talking about. Okay. Now you will mark all the centers in this atoms and join them. What kind of geometrical figure does it form? Straight line. So this kind of packing is called linear. Now let us take one atom as the reference atom. Let us take this one. So this atom is contact with how many atoms? 1, 2. So coordination number for this kind of linear packing is 2. Okay. So this is the only possible one-dimensional packing we are going to talk about. Next is packing in 2 dimensions. First thing is square closed packing. So square closed 2 dimension means there will be 2 directions, x direction, z direction. So first I will go in x direction like this and then z direction. Okay. Okay, I can take another one like this. So now if you see, this is square close packing. It has its dimension in z direction, it has its dimension in x direction. So that is why it is a packing in 2 dimensions. Now again, if you take the centers of each atoms over here and join. See, it is forming squares, right? So that is why it is called square close packing. Next is coordination number. If I take this atom as a reference, this is in contact with 1, is not in contact with this atom, 2, 3, 4. Okay. So coordination number of this kind of packing is 4. Next is hexagonal closed packing. Okay. Now again we will draw the, first we have to mark the centers and let us join them. What is it for? Regular hexagon. So that is why it is called hexagonal closed packing. Let us take a reference atom, this one. So it is connected or it is attached with all these 6 atoms. So coordination number of this kind of packing is 6. Clear? So see, we have completed packing in 1D and packing in 2D. Next क्या है? 3D. चलो, we'll do 3D right now. So now we'll be doing packing in 3 dimensions. We have understood what is packing in 1 dimension. We have understood what is packing in 2 dimensions. Now we'll do what is packing in 3 dimensions. See, simple cubic. What are the two? There are 2 types of 3D packing. So first thing is simple cubic. Simple cubic means there is a first layer. After that there is a second layer. There is a third layer. Obviously you can say, sir, this is Z axis, this is X axis. But from the 3D comes. There is, this layer is getting continued. So behind this there is another one. Behind this there is another one. You can see this kind of things very difficult. But well, bricks. If you see bricks, 1 brick, 2 brick, 3 brick like this. So if you see the bricks are placed one above other. So this is simple cubic packing. So 1 brick is 1 atom if you can take. I know it's not round, but still if you take 1 brick is 1 atom, then put some 6 bricks and below that or above that you put bricks. So that is simple cubic packing. Okay? Now, if you see, what is the coordination number of this kind of packing? Let's take a reference cell again, reference atom. So here we can see 1, 2, 3, 4. But what about the y-axis? In this, above the board, there will be another atom which will be touching this atom, and behind the board there will be another atom which will also be touching this atom. So coordination number will be 6 in case of simple cubic type of packing. What will the packing fraction? Just now we did, the last video, that the packing fraction of the simple cubic type of lattice is 52%. Okay. Now we come to hexagonal closed packing. What is hexagonal closed packing? So first of all you have to understand, we have already discussed about hexagonal closed packing while calculating the packing fraction. Now I'll just draw one reference cell over here, and this is hexagonal closed packing. If you see, okay. Now, if you see, here one atom is surrounded by 6 atoms that we can see over here. Now, how do we compare this with the simple cubic type of packing? So first of all, let us draw the extended structure of hexagonal closed packing. So things are much more clear to us. And here again, we will draw one hexagon, and here there will be this little bit inclined, but okay. So this is hexagonal closed packing. So if you see over here, this 3 is placed in which place? So here also there is one atom. So this 3 is placed in between the crevices created in between these atoms. So here if you see, there are crevices created over here, right? These crevices are called voids. These crevices are called voids. Okay. So okay. So if you see, this is the primary structure of hexagonal closed packing. All the atoms are not equal. I'm sorry for that. Okay. Now you can easily say by joining this center, this is hexagonal. Okay. Now see, there is some crevices created in between them. Okay. This is the crevices I am talking about. Okay. So if you see this crevice, this one, okay, this is an upside down triangle and this is an upright triangle. Again, this is an upside down triangle and again this is upright triangle. Again, this is an upside down triangle. So let us take these upright triangles, wherever this upright triangle, as void 1, and let us take this upside down triangles as void 2. Okay, these are called voids. So within this, the next layer will be getting formed. So I can put one atom over here like this. Okay, one atom over here, because there will be, the atom can be fixed in these crevices. Next atom also I can put over here. Okay. So if you see, if I put atoms in void 2s, okay, void 2s, then I cannot put atom in void 1 because the space is occupied over here. I cannot put another atom in the same layer in void 1 because the space is occupied. The space is getting occupied. Okay. So there can be one possibility that these atoms are occupying void type 2 or these atoms are occupying void type 1. Okay. So here also I am drawing the cells because we are talking about void type 2 over here. Okay. Now if you see, in this part we have drawn a second layer. This part. And this part we have not drawn a second layer. And this is void type 1. This is void type 2. At this moment, if you put one atom over here, then what is the exact structure of this? It is like this, right? Okay. And here is the void where it is getting put. Are you understanding this? Okay, I'll draw it again. This is the kind of void on which you are putting another atom. Okay, so there are 4 atoms. In between them, there is some space. That space is called tetrahedral void. Okay, because it is surrounded by 4 atoms. Okay, now here if you see, I have drawn a second layer, correct? I have drawn a second layer. You see, this is the second layer that I have drawn. Okay. After drawing second layer, I have identified another void over here, right? Now if you see this void, then this void, on the top of this void, here there is a upside down type of lattice, right? Upside down type of triangular lattice like this at the top. Okay? And what is at the bottom? Bottom there is this one. This cell, this cell and this cell. So there is this type of thing at the bottom. So how many total number of cells is in touch with this void, this newly created void in the second layer? 6 number of cells. That is why the void created in the second layer, which surmounts the first layer, is called octahedral void. It is surrounded by, octahedral void is surrounded by 6 atoms. That is why in case of octahedral void the coordination number is 6. In case of tetrahedral void the coordination number will be 4. So voids also have a coordination number. How many atoms is surrounding the void? If this is 4, then it is tetrahedral void. If it is 6, then it is octahedral voids. Octahedral voids are only formed when there will be second layer. Okay? Okay. So that is basically giving you the idea of basic idea of the voids. We will go much detail into voids basically, but more or less coordination number they ask, so that is why I covered it up. And you also understand what is hexagonal closed packing. Okay? Voids also you understand right now. Tetrahedral voids will be coordination number will be 4. Octahedral voids coordination number will be 6. Okay? Okay. Now next is there are two kinds of hexagonal closed packing we are going to discuss. We are going to discuss in the next video, maybe tomorrow. Okay, so that will be it, I guess, for today. You understand what is tetrahedral void, you know what is octahedral void. Try to rewind and understand more and more so that you can do problems also on this. We will discuss problems, lot of problems in the offline class, obviously. So, okay. Another thing I want to discuss, while we discussed about 2D packing. Okay, 2D packing. Each void over here was surrounded by 1, 2, 3 atoms. It is called triangular void. Triangular void coordination number is 3. Okay? So we learnt about triangular void, we learnt about tetrahedral voids, coordination number 4 surrounded by 4 atoms, forms a structure like tetrahedron, and tetrahedral void is basically, this is the structure of tetrahedron. Okay? And in case of octahedral voids, it is a structure of octahedron. Okay, it's a structure of octahedron. Okay, you can go through your book. They have given very good 3-dimensional picture, which is very difficult to show on board. But you go through your book for the picture, and if you find any problems, obviously, and then okay. So basically, if you see an octahedral void, then this equilateral triangle is upright and this equilateral triangle is upside down. So one equilateral triangle, if one equilateral triangle is like this, then the bottom one is like this. Okay, so that is, and in between the space will be octahedral void. Tetrahedral void coordination number is 4, octahedral void coordination number is 6. Okay? There is two kinds of hexagonal closed packing. One is body centered type, another is cubic closed packing. So both of them we will be discussing in the next video. So अभी के लिए इतना ही ठीक है. So you complete all these theories, and after that maybe tomorrow I'll do this different types of body centered closed packing, cubic closed packing. And body centered cubic packing is there. There will identify another kind of void that is called your cubical voids. Okay, and okay, there is a homework for you. Please calculate the packing fraction of square closed packing and hexagonal closed packing in 2 dimensions. ठीक है, बहुत easy है. That you have to do as a homework for today. And after that, we will go into much more detail of your different types of voids, that is octahedral and tetrahedral, distances between them, number of cells, and little bit complicated ones also will do. Okay, thank you very much.